Today I am giving my lecture on paper number 108, Linear Algebra, Unit 4, topic Angle between two non-zero vectors, Orthogonality, and we see the Pythagoras Theorem. And now we start with angle between two non-zero vectors. Definition: an angle theta between two non-zero vectors x and y is given by cos theta is equal to inner product x with y upon norm x into norm y, where theta is 0 is less than or equal to theta less than or equal to pi. Now we see the example on angle between x and y. Find the angle between x and y in each of the following cases. First example, x is equal to 3, 0, y is equal to 5, 5. Solution: let x is equal to 3, 0 and y is equal to 5, 5. Here inner product x with y is equal to define x dot y. So dot product of 3, 0 with 5, 5 is equal to 3 into 5 plus 0 into 5 is equal to 3 into 5 is equal to 15 plus 0. So 15 plus 0 is equal to 15, and norm x is equal to inner product x with x under root inner product x with x. Norm x is equal to inner product x with x under root, so is equal to under root 3, 0 into 3, 0, so is equal to 3 square plus 0 square. So this under root 3 square is equal to 3, because norm is always greater than or equal to 0, and norm y is equal to under root 5 square plus 5 square. So 25 plus 25 is equal to 50. So under root 50 is equal to 5 under root 2. Now cos theta is equal to inner product x with y upon norm x into norm y. We have inner product x with y is equal to 15. Norm x is equal to 3, and norm y is equal to 5 under root 2. So 15 upon 3 into 5 into under root 2. So 5 into 3 is equal to 15 into under root 2. So this is equal to under 1 upon under root 2. Cos theta is equal to 1 upon under root 2. So theta is equal to cos inverse 1 upon under root 2. So we get theta is equal to pi by 4. Now we see the next example for the value x is equal to 1, 0 and y is equal to 0, 1. So inner product x with y is equal to x dot y. So is equal to 1 into 0, 1 into 0 plus 0 into 1. So 1 into 0 is equal to 0 plus 0 into 1 is equal to 0. So inner product x with y is equal to 0, and norm x is equal to under root 1 square plus 0 square is equal to 1 and norm y is equal to under root 0 square plus 1 square is equal to 1. So now cos theta is equal to inner product x with phi upon norm x into norm y. But here we have norm xy is inner product x with y is equal to 0 upon 1 into 1. So 0 upon 1 is equal to 0. So theta is equal to cos inverse 0. So we get theta is equal to pi upon 2. Now orthogonality definition. Here we see the definition of orthogonal to each other. We say x and y are orthogonal to each other if inner product x with y is equal to 0. Here we let V be an inner product space and x y belongs to V, then we can say that x and y are orthogonal to each other if inner product x with y is equal to 0. In this case, we write x orthogonal y and y is orthogonal to x. Here V is inner product space and two element x and y belongs to V. Then we say that x and y are orthogonal to each other if inner product x with y is equal to 0. Then we write x is orthogonal to y or y is orthogonal to x. Now example, show that the vector x is equal to minus 3 comma 4 and y is equal to 6 comma 4 into 5. In this, in R square are orthogonal to each other. So solution, inner product x with y is equal to x dot product y. X is equal to minus 3 comma 4 dot product y is equal to 6 comma 4 into 5. So now we take dot product of this vector minus 3 into 6 plus 4 into 4.5. So this is minus 3 into 6 is equal to minus 18 plus 4 into 4.5 is equal to 18. So minus 18 plus 18 is equal to 0. So inner product x with y is equal to 0. So x and y are orthogonal to each other. Theorem 1. Theorem 1. Let V be an inner product space and let x belongs to V be fixed. Then the set V belongs to V such that inner product x with V is equal to 0 is a subspace of V. This set is denoted by x orthogonal. Proof. Let x belongs to V. We have to prove that the subset x orthogonal is equal to V belongs to V such that inner product x with V is equal to 0 of V is a vector subspace. So we let V1 and V2 belongs to x orthogonal and alpha beta belongs to R. So we have to show that alpha V1 plus beta V2 belongs to X orthogonal. So here we have V1 and V2 belongs to X orthogonal. So V1 belongs to X orthogonal implies X in the inner product X with V1 is equal to 0, and V2 belongs to X orthogonal implies inner product X with V2 belongs to is equal to 0. Now we have to show that inner product X with alpha V1 plus beta V2 is equal to 0. So this belongs to X orthogonal. So now inner product X with alpha V1 plus X with beta V2. Now using property of inner product, alpha into inner product X with V1 plus beta into inner product X with V2. But inner product X with V1 is equal to 0, and X with inner product X with V2 is equal to 0. So alpha into 0 is equal to 0 plus beta into 0 is equal to 0. So is equal to 0. So inner product X with alpha V1 plus beta V2 is equal to 0. So here alpha V1 plus beta V2 belongs to X orthogonal. Hence X orthogonal is a subspace of V. Now second theorem, let two non-zero vectors in inner product space V, let V and W be two non-zero vectors in an inner product space V. Here V and W be non-zero vectors in an inner product space V. If both are orthogonal, V orthogonal W, take here we have given V and W both non-zero vectors in an inner product space V, and both are orthogonal. Then we have to show set V and W is linearly independent. So we have given uh, V and W non-zero vectors, and V is orthogonal to W. So inner product V with W is equal to 0. So we have to prove that set V and W is linearly independent set. So let alpha and beta belongs to R be such that alpha V plus beta W is equal to 0 vector. Then norm alpha V plus beta W is equal to 0. So uh, squaring both the side, norm alpha V plus beta W whole square is equal to 0. So we can write in inner product space alpha V plus beta W, and with alpha V plus beta W is equal to 0. So simplifying this, we get alpha V square norm alpha V square plus 2 inner product alpha V with beta W plus norm beta W square is equal to 0. Now alpha square common into norm V square plus 2 alpha beta inner product V with W plus beta square into norm W square is equal to 0. Here we have given V is orthogonal to W. So inner product V with W is equal to 0. So this is equal to 0. So alpha square into norm V square plus beta square into norm W square is equal to 0. So this equal to 0. Both the term alpha square into norm V square and beta square norm W square both are non-negative. Therefore both must be 0. So alpha square into norm V square is equal to 0 and beta square norm W square is equal to 0. But V and W are non-zero vectors. We, we have given V and W are non-zero vectors in inner product space. So norm V not equal to 0 and norm W not equal to 0. So alpha square and beta square must be 0. So alpha square is equal to 0 and beta square is equal to 0, which implies alpha is equal to 0 and beta is equal to 0. Here alpha and beta both are 0. So this set V and W is linearly independent. Now the next theorem, let V be an inner product space and X belongs to V if X is orthogonal to all vectors in V, then X is equal to 0 vector. Here we have given V be an inner product space and X belongs to V if X is an orthogonal to all vectors in V, then X is equal to 0 vector. Proof: given that X belongs to V is an orthogonal to each vector in V. In particular, X is orthogonal to X, which implies inner product X with X is equal to 0. So norm X square is equal to 0 and norm X square is equal to 0 implies X must be 0 vector. Hence the proof. Now definition: let V be an inner product space and S be any non-empty subset of V. Let V be an inner product space and let S be any non-empty subset of V. A vector V belongs to V is said to be orthogonal to S if inner product V with S is equal to 0 for every S belongs to V. Let any inner product space and let any non-empty subset of V. A vector V belongs to V is said to be orthogonal to S if inner product V with S is equal to 0 for every S belongs to S. Now definition, another definition: V be an inner product space and let S be any non-empty subset of V, then this set V belongs to V such that inner product V with S is equal to 0 for every S belongs to S is called orthogonal complement of S, and it is denoted by S orthogonal. As let V be an inner product space and let S be any non-empty subset of V, then the set V belongs to V such that inner product V with S is equal to 0 for every S belongs to S is called orthogonal complement of S, and it is denoted by S orthogonal. Let theorem 4, let V be an inner product space and S be any non-empty subset of V. Let V be an inner product space and S be any non-empty subset of V, then S orthogonal is a subspace of V. Proof. We have to prove that the subset S orthogonal is equal to V belongs to V such that inner product V with S is equal to 0 for every S belongs to S of V is a vector subspace. So let V1 and V2 belongs to S orthogonal and alpha beta belongs to R. So to show alpha V1 plus beta V2 belongs to S orthogonal. So let V1 belongs to S orthogonal implies inner product V1 with S is equal to 0 for every S belongs to S, and V2 belongs to S orthogonal implies inner product V2 with S is equal to 0 for every S belongs to S. Now for any S belongs to S, inner product alpha V1 plus beta V2 with S is equal to inner product alpha V1 with S plus inner product beta V2 with S. So alpha into inner product V1 with S plus beta inner product V2 with S. But inner product V1 with S is equal to 0 and inner product V2 with S is equal to 0. So this is equal to 0 and this is equal to 0. So this is equal to 0. So it shows that alpha V1 plus beta V2 belongs to S orthogonal. Hence, S orthogonal is a subspace of V. Now, theorem, Pythagoras theorem, let V be an inner product space and xy belongs to V, then x orthogonal y if and only if norm x plus y square is equal to norm x square plus norm y square. Proof. Suppose x is orthogonal to y, then inner product x with y is equal to 0. Now norm x plus y square is equal to norm x square plus 2 into inner product x with y plus norm y square. Here we have given x is orthogonal to y, so inner product x with y is equal to 0. So inner product x with y is equal to 0. So is equal to norm x square plus norm y square. Now conversely, suppose norm x plus y square is equal to norm x square plus norm y square. Then norm x plus y square is equal to inner product x plus y with x plus y is equal to norm x square plus norm y square. So norm x square plus 2 into inner product x with y plus norm y square is equal to norm x square plus norm y square. So norm x square cancel out, norm y square cancel out. So 2 into inner product x with y is equal to 0. So inner product x with y is equal to 0. So x is orthogonal to y. Now the next theorem, let V be an inner product space and xy belongs to V, then x minus y is orthogonal to x plus y if and only if norm x is equal to norm y. Here given that x minus y is orthogonal to x plus y if and only if inner product x minus y with x plus y is equal to 0 if and only if inner product x with x plus inner product x with y minus inner product y with x minus inner product y with y is equal to 0. So here inner product x with y minus inner product y with x cancel out. So if and only if inner product x with x minus inner product y with y is equal to 0, and inner product x with x is equal to norm x square minus inner product y with y is equal to norm y square is equal to 0. So if and only if norm x square is equal to norm y square, if and only if norm x is equal to norm y. This is complete the proof. Now see the definition of orthogonal set. Let V be an inner product space. A subset S of V is said to be an orthogonal set if 0 vector does not belong to S and inner product x with y is equal to 0 for every xy belongs to S with x is not equal to y. In this definition, first case 0 vector does not belongs to S, and second condition inner product x with y is equal to 0 for every xy belongs to S with x is not equal to y. Example, show that a subset S is equal to 2, minus 3, 0 and 6, 4, 3 of R3 is an orthogonal set. Solution. Uh, we say S1 is equal to this and S2 is equal to this. So here S1 and S2 not 0 vector in R3. Therefore, the first condition 0 vector in R3, 0 vector does not belongs to this subset, and now S1 S2 is equal to inner product x1 with s1 with s2 is equal to dot product of 2, minus 3, 0 with 6, 4, 3. So dot product 2 into 6 plus minus 3 into 4 plus 0 into 3. So 6 into 2 is equal to 12 minus 3 into 4 12 plus 0. So 12 minus 12 is equal to 0. So inner product S1 with S2 is equal to 0. So this set is orthogonal set in R3. Next definition: a basis of an inner product space is said to be an orthogonal basis if it has an orthogonal set. And now the theorem: any orthogonal set is an inner product space is linearly independent. So let us see the proof. Let V be an or V be an inner product space, and let set S is equal to V1 V2 up to Vk be an orthogonal set in V. Then all sets are not equal to 0 vector for all set Vi is not equal to 0 vector for every 1 is less than or equal to I less than or equal to k, and inner product Vi with Vj is equal to 0 for every 1 is less than or equal to I and j is less than or equal to k with I is not equal to j. So here we have to show that S is linearly independent set. So we assume that summation I is equal to 1 to k alpha I Vi is equal to 0 vector where alpha I belongs to R and 1 is less than or equal to I less than or equal to k. Then for any Vj belongs to S, we have inner product summation I is equal to 1 to k alpha I Vi with Vj is equal to this is 0 vector. We assume so 0 inner product 0 vector with Vj is equal to 0. So now put the value of summation 1 equal to I is equal to 1 to k alpha I V I with Vj is equal to alpha 1 V inner product alpha 1 V1 plus alpha 2 V2 plus up to alpha j Vj plus up to alpha k Vj with alpha k Vk with Vj. So this is equal to 0. So this equal to 0 equal to alpha 1 inner product alpha 1 V1 with Vj and common out alpha 1. So inner product V1 with Vj plus alpha 2 inner product V2 with Vj plus up to alpha j Vj with Vj plus up to alpha k Vk with Vj. So uh, by 2 I is equal to j, this is not equal to 0, but inner product V1 with Vj, inner product V2 with Vj up to inner product Vk with Vj all are 0. So multiplying with alpha 1, this is equal to 0 and this is equal to 0 and this is equal to 0. So remaining is alpha j Vj with inner product Vj with Vj. So this is equal to 0. Now by 1, Vj is not 0 vector. So this is not equal to 0. So alpha j is equal to 0. Since alpha j is arbitrary, we have alpha I is equal to 0 for every 1 is less than or equal to I, less than or equal to k. It means that set is linearly independent. Now we see the example for let V be an inner product space. Let set E is equal to V1, V2 up to Vn be an orthogonal basis of V if V is equal to summation I is equal to 1 to n alpha I Vi, then alpha I is equal to inner product V with Vi upon inner product Vi with Vi. 1 is less than or equal to I, less than or equal to n. Solution: given that E is an orthogonal basis of V, so by definition of orthogonal basis, Vi is not equal to 0 vector for every 1 is less than or equal to I, less than or equal to n. And second, inner product Vi with Vj is equal to 0 for every 1 is less than or equal to I and j less than or equal to n with I is not equal to j. Now for 1 less than or equal to I, less than or equal to n, inner product V with Vi is equal to inner product j is equal to 1 to n alpha j Vj with Vi. So we expand the summation and we get alpha 1 V1 with alpha 1 into inner product V1 with Vi plus alpha 2 inner product V2 with Vi plus up to alpha I into Vi with Vi plus up to alpha n Vn with Vi. By this condition, alpha I inner product Vi with Vi are non-zero, remaining all are 0. So is equal to alpha I inner product Vi with Vi. But Vi is not 0 vector. So inner product not equal to 0. So alpha I is equal to inner product alpha I is equal to inner product V with Vi upon inner product Vi with Vi, and 1 is less than or equal to I, less than or equal to n.